Hello and welcome back to the next rubber duck physics video. A.4 here. We have covered a lot already. Angular displacement, angular velocity, angular acceleration, torque, and even rotational energy. But there is still one more missing piece to our puzzle, something to connect to linear momentum. And you guessed, it's angular momentum. Today we are going to learn all about angular momentum and why it's so important. We'll see how it relates to everything we have been building so far, and of course, our rubber ducks are ready to help us spin through this topic. Let's get started. Before we jump in, let's do a quick recap. Throughout our journey, we have been making connections between linear and angular quantities. We have seen that linear displacement matches up with angular displacement. Linear velocity has an angular twin, angular velocity, omega. Linear acceleration, A, connects to angular acceleration, alpha, and force plays a similar role to torque, tau. But there is still one thing missing. Linear momentum, P equals m times v, mass times velocity. We have talked a lot about how forces affect linear motion and how torque affects rotational motion. But where is the rotational counterpart for momentum? That's what we are here to discover today. Now it's time to meet our new star, angular momentum, L, capital L. Angular momentum is to rotational motion what linear momentum is to straight line motion. We know that linear momentum is defined as the mass times velocity, P equals m times v. So what does angular momentum look like? Well, it's a bit more involved. Instead of mass, we use moment of inertia, I. And instead of linear velocity, we use angular velocity, omega. The formula is, therefore, L for angular momentum equals I times omega. Angular momentum depends on how hard it is to spin the object, that's the moment of inertia, and how fast it's spinning, that's the angular velocity. So I, not meaning myself, and omega together give us L. One thing to keep in mind is that just like with linear momentum aligns with the velocity vector, angular momentum will have the same positive or negative direction as the angular velocity of the object, depending on the direction of the spin. If the spin is counterclockwise, angular momentum is positive. If it's clockwise, it's negative. Let's place one of our ducks on a rotating platform. We'll spin it clockwise, and that gives it negative angular momentum. Now let's reverse it and spin counterclockwise, and we have got positive angular momentum. Simple, right? Notice that angular momentum is defined even for a point-like object moving in a circle, as both moment of inertia and angular velocity are defined for it. What's the unit to measure angular momentum in? Let's substitute units of the quantities in its definition. Moment of inertia is measured in kilograms meter squared, omega in radians per second, therefore the unit of angular momentum is kilograms meter squared per second with an invisible 1 for radians. This unit is also left without its own name so far, so if you become a renowned rotational motion scientist, you may be entitled to come up with some new name for it. It will be okay to select your own family name if you want. Just don't forget to work out a short version if it's more than 2 syllables long. So why is angular momentum a little more complicated than linear momentum? It's because in linear momentum, all parts of an object move in the same direction. So it's easy to say P equals m times v vector, there is only one v vector. In rotation, different parts of the object are moving in different directions and at different speeds. That's why we use I, the moment of inertia, instead of just mass. Angular momentum captures not just the mass, but also how it's distributed around the axis. And in more than just a few cases, this distribution can change even without mass being added to or removed from the object or system. Now that we know what angular momentum is, let's talk about one of its most important properties, conservation. Just like linear momentum, angular momentum is conserved, which means it stays the same as long as there is no resultant external torque acting on the system or object. if nothing from the outside is pushing or twisting the object, or if such effects upon it cancel out, its total angular momentum stays constant. This leads to surprising consequences in case the object's or system's mass distribution changes due to forces internal to it, under the effect of no external resultant torque. Because the value of I has, let's say, decreased, omega now has to increase to keep L strictly constant. And that's what will actually happen, sometimes against all expectations. Imagine figure skaters spinning. When they pull their arms in, they decrease their moment of inertia, I. Because L equals I times omega has to stay the same, their angular velocity, omega, increases, and they spin faster. When they stretch their arms out, I increases, and they slow down. The key here is that no one from the outside is pushing or pulling or spinning them. They are just changing the way their mass is distributed with respect to their axis of rotation. And a change in I changes omega to keep L constant. It's almost like they are controlling their speed without touching anything. Angular momentum conservation shows up all over the place. Ever wonder why Earth's spin doesn't just stop? It's because there is no external torque acting on it from space. That's why it keeps spinning. Good for us. Think about a gymnast or a diver. They tuck their body in midair to spin faster, and then they stretch out to slow down. They are controlling their moment of inertia, I, to change their spin rate, omega, without any external help. Or if you have ever been on the frequently mentioned merry-go-round, you have seen this in action. When kids stand at the edges and then move inward, the merry-go-round spins faster. They are changing I, which changes omega, but L stays the same. No one needs to push the merry-go-round to make this happen. The surprising thing is, in all these cases, it looks like an external force was applied to speed up or slow down the rotation. But there wasn't. It was just about how the mass was distributed. Alright, we have seen how angular momentum behaves when objects spin freely. But what happens when two spinning objects interact? What if one speeds up the other? Imagine, for example, two ice skaters on the rink. They are both spinning, but what happens when they grab hands and starts to spin together? Or if one of them throws a ball to the other? In our next video, we are going to explore angular momentum transfer. What happens when two objects meet and exchange their spin? It's going to be fun, and I'll see you there. If you have enjoyed this introduction to angular momentum, make sure to watch the next video, where we'll dive deeper into how it plays out in different interactions. Plus, we will solve a few more exercises related to the content of the whole chapter. By the way, I am also available for tutoring in IBDP physics and other high school physics courses. Check out my YouTube channel description for contact details if you are interested. Thanks for watching. See you next time.